You find yourself in a beautiful garden staring at a sunflower it towers over you. Pretty cool stuff, right? I mean, yeah, I guess it's just a sunflower though, dude. Chill. Now, prepare to have your mind blown. That sunflower follows a mathematical pattern that's been there since sunflowers first existed. But it took until medieval times for someone to actually figure out the maths behind it. And it's not just sunflowers. We're talking about pine cones, pineapples, seashells, hurricanes, and yes, even entire galaxies. Today we're going to discover the natural world is not just beautiful, but it's beautiful because it's running the same calculations for billions of years. From the smallest living cells to spiral galaxies, certain number patterns appear with surprising regularity. What's that Jim Carrey movie? The number 17 or whatever? God, that was shit. No disrespect, Jim Carrey. Ace Ventura is excellent. These patterns follow clear mathematical rules that can be described and calculated. A sunflower offers one of the most striking examples. In its seed head, spirals curve in two opposing directions. Counting them often shows you numbers like 34, 55, or 89. These values belong to a famous mathematical sequence described in Europe more than 800 years ago. Some of these sequences, like the Fibonacci numbers and the golden ratio, are well known. Others, such as Lucas numbers and Pascal's triangle, are less familiar. Together, they reveal how the same mathematical principles govern phenomena that seem completely unrelated. The Fibonacci sequence is one of the most recognizable mathematical patterns in nature. It links the arrangements of seeds, leaves, and other structures to simple mathematical rule that has been studied for centuries and has become a key example of how mathematics can guide growth. The sequence begins with two numbers, 1 and 1. Each number is then the sum of the two before it, producing a pattern meaning 1, 1, 2, 3, 5, 8, 13, 21. You see how it goes, and it doesn't end because numbers don't end. The simple rule is connected to patterns observed in nature. Although most people associate the sequence with Leonardo of Pisa, known as Fibonacci, its origins are actually much older. Through the Islamic world, these ideas were preserved, studied, and then passed over to Europe. In 1202, Fibonacci published Liber Abaci. I don't know about the pronunciation on that. Didn't do very well at Latin in school. Using the sequence to model the growth of a hypothetical rabbit population. While the example popularized the numbers, their applications extend far beyond it. Phyllotaxis, the arrangement of leaves, seeds, or petals around a stem, often follows the Fibonacci sequence. Many plants grow at angles that produce spirals when viewed from above. The number of spirals in each direction commonly matches the consecutive Fibonacci numbers, so seeds fill the available space properly. Pine cones with their overlapping scales and pineapples with the diagonal surface rows follow the same rule. Certain shells also grow in curves and are linked to ratios in the sequence. Just a quick break before we continue to tell you about today's sponsor, Sheath Underwear, the most comfortable boxer briefs I've ever worn. In fact, I'm wearing them right now. Ugh, not anymore. Obviously not, that's not how it works. But yeah, I just had these tucked into the back of my trousers. But as well as that, I do have sheath on underneath with my trousers because I like sheath and I wear it. In summer especially, I don't know, you just be walking around and you're like, oh, it's sweaty, it's hot. We finally got some nice weather here. I'm probably a little sweaty under the arms, in fact. And I'm wearing my sheath and I'm just like, oh, it just keeps everything separate and nice. They've got these different compartments so, you know, your man bits can be separated from each other. They don't get all sweaty and you get that, I don't know, when I was a kid we'd call it crotch rot. So, sheath fixes that. Now, you might be skeptical. I was definitely skeptical at first. I'm like, I'm not going to really like this, but I'll give it a go. I remember when Sheath first sponsored, and I was like, send me some for free, Sheath. I'll try them, and then we'll talk, all right? And then we talked. I tried them, we talked, and I was like, yes, please, let's do that. They've even got bamboo and new mesh options for extra cooling. Hey, I'm wearing the mesh ones. Go to sheath.com/sideproject and use the code sideprojects for 20% off your order. That's sheath.com/sideprojects. Code sideprojects. 20% off. The golden ratio is a mathematical proportion that appears in certain patterns, structural arrangements, and spirals found in nature. Its connection to the Fibonacci sequence has also made it one of the most studied numerical relationships in both mathematics and biology. The golden ratio, often represented by the Greek letter phi, is approximately equal to 1.6180339887. And no, I didn't remember that. I'm reading off a teleprompter in case you couldn't guess. It describes the relationship between two quantities where ratio of the larger to the smaller is the same as the ratio of the combined total to the larger. A simple way to picture this is to imagine a stick cut into two pieces. One is longer, the other is shorter. If the length of the whole stick divided by the longer piece is the same as the longer piece divided by the shorter piece, the lengths are the golden ratio. This proportional representation can be written as A plus B over A equals A over B, where A is the larger segment and B is the smaller. The golden ratio and the Fibonacci sequence are closely linked. As the Fibonacci sequence progresses, the ratio of each term to the one before it moves closer to phi. For example, 21 divided by 13 is approximately 1.615, while 34 divided by 21 is approximately 1.619. As the numbers get larger, the ratio approaches 1.6180339887. This link means that patterns shaped by the Fibonacci sequence often also reflect proportions associated with the golden ratio. It appears in many natural contexts. Certain shells, including the chambered nautilus, coolest name for a shell, grow in spirals whose expansion rate approximates phi. The arms of some spiral galaxies follow curves that reflect a similar proportion. Hurricanes sometimes form spirals close to this ratio in their geometry, and branching patterns in plants also do. There's also arrangements of flower petals and seed spacing in some fruits that can approximate it. Some proportions in animal bodies, such as spacing of features in certain species, can reflect this ratio, although these cases are often less than perfect. The golden ratio has attracted a reputation that extends far beyond mathematics. Over the years, it has been credited with shaping some of history's most famous buildings, influencing art across centuries, and even determining the proportions of the human body. Many of these claims have been repeated so often that they're accepted without question. Examining them closely shows us which ones are supported by evidence and which are kind of just made up. The golden ratio is often presented as a flawless blueprint behind everything from human anatomy to the world's greatest monuments. Popular claims include the Great Pyramid of Giza, the Parthenon, Leonardo da Vinci's Vitruvian Man, even Simon Whistler's face, and Michelangelo's David. Apparently, they were all intentionally created to match phi exactly. It's also said that human faces, from the spacing of the eyes to the length of your nose, follow the ratio in ideal form. In nature, examples are often expanded beyond the familiar to include the spiral of a nautilus shell, the growth of Romanesco broccoli. Alright. Didn't even know there was a type of Romanesco broccoli. The curve of a kudu's horns, the pattern of seeds in that garden sunflower we mentioned earlier, the one that I think it was Jay who wrote the script, got a little bit overexcited about, and even the path of hurricanes, which is actually exciting and terrifying. These are frequently presented as perfectly matching phi, as though the ratio is a universal law of beauty and structure. Measurements show that many of these famous examples do not align with the golden ratio as closely as often claimed. The Great Pyramid's proportions vary depending on how measurements are taken, and there is no historical record proving its design was based on phi. The Parthenon's dimensions differ enough from the ratio that it cannot be considered a deliberate match. Vitruvian Man and Michelangelo's David show proportional harmony, but not consistent phi relationships across all features. Human faces and bodies exhibit wide variation, meaning only a small percentage align closely with the ratio. In nature, the spiral of a nautilus shell is a logarithmic spiral that only loosely resembles the golden spiral. Romanesco broccoli follows a fractal pattern rather than phi, and the curvature of kudu horns is shaped by growth biology, not mathematics. Even hurricanes form under atmospheric conditions that do not reliably match phi spiral. While phi can appear in biological and physical processes, its presence is situational rather than universal. The golden ratio isn't a universal law, but when it appears in nature, it often serves a practical purpose. Its link to both beauty and functionality comes from how it can organize space efficiently while maintaining structural strength. In plants, growth patterns related to phi can help distribute leaves or seeds so each gets maximum sunlight or space, reducing competition. Certain flowers like lilies or daisies show arrangements that approach the ratio because they allow for denser packing without overlap. In animals, spiral patterns in horns or shells sometimes follow proportions close to phi, creating strong and lightweight structures. Even in physics, patterns that resemble the golden ratio can help manage forces evenly, as in some crystal formations. When conditions favor efficiency, stability, and resilience, phi may emerge as a natural outcome, because the same proportions that humans find attractive can also be energetically effective. Fractals are patterns that repeat at different scales. A small part of the pattern looks similar to the larger whole, and this repetition is seen in many natural and physical systems. They form when the same process occurs again and again, whether in the branching of a tree, the course of a river, or the path of lightning through the air. Fractals demonstrate how repeating rules can produce structures that are both visually striking and highly functional. A fractal is a self-similar pattern. This means that its structure is repeated at progressively smaller or larger scales. This property can continue for several layers of detail, creating patterns that appear consistent no matter the level of magnification. In mathematics, fractals are generated when a simple operation is applied repeatedly, with each result becoming the starting point for the next step. Now, if you think all of that sounds a bit like science fiction, it's a bit like over my head, well, you're about to discover that nature is obsessed with this stuff. You see, the same effect happens when growth or physical processes follow unchanging rules at each stage, such as the way ice crystals expand in freezing water, or how plants add new growth along a repeating pattern of angles. Fractals can be found in many areas of nature, such as the Romanesco broccoli, which produces a series of spiral, cone-shaped florets, with each cone made of smaller cones that repeat the same shape. Another example is in fern leaves, which divide into smaller fronds, and each frond mirrors the form of the entire leaf. Additionally, coastlines display repeating jagged outlines and form a satellite image of an entire shoreline down to the edge of a single rock pool, while the shape retains a similar irregularity, which is insane. That's so cool. Lightning branches into smaller and smaller forks, each following the same structure as the main bolt. Snowflakes grow from a central hexagonal crystal, and each arm repeats the same branching structure at different scales. Tree branches, river networks, and even the bronchial tubes in human lungs all follow the same pattern, showing the magnitude of fractals in nature. In mathematics, fractals often emerge from a process known as iteration, where the same equation or geometric transformation is applied repeatedly. The Mandelbrot is a famous example of this, generated from a simple formula but producing patterns of extraordinary complexity that just repeat endlessly. In nature, fractal growth does not require complicated instructions. For example, the angle at which a tree branch splits from its trunk might remain constant as the tree grows, and the same angle can appear again when that branch divides into smaller branches. Similarly, river networks form when water follows paths of least resistance, splitting into smaller channels in a way that mirrors the main river's path. In both these cases, a single repeating rule produces an intricate structure. So why does nature build with fractals? Well, they offer practical advantages in nature, as by repeating a pattern, an organism or system can increase its surface area without requiring more overall volume. In plants, this means better access to sunlight, as the layered fern fronds or finely divided leaves for dill or carrot plants and root systems branch out to reach a greater volume of light, oxygen, and nutrients. In animal circulatory systems, blood vessels branch out to get nutrients to every single cell. Fractals are also important in systems like river basins, where a branching network allows rainfall to be collected from a wider area and delivered to the main channel. In atmospheric systems, storm clouds and weather fronts show fractal edges, which influence how energy and moisture are transferred over large distances. Even in geology, fractal patterns in rocks or in crack networks in the ice sheets display fractal properties, showing how repeating stresses shape a landscape. By following the same pattern on multiple scales, these systems show resilience and adaptability with minimal wasted energy. Prime numbers seem like an abstract mathematical concept, and yet they appear in biological strategies that have developed over millions of years. Certain species use prime-numbered intervals in their life cycles, and this unusual timing can make the difference between survival and extinction. A prime number is a whole number greater than 1 that has no divisors other than 1 in itself. Examples include 2, 3, 5, 7, 11, and 13. You know what prime numbers are, and if you don't, did you go to school? Unlike composite numbers, which can be factored into smaller integers, prime numbers cannot be broken down in this way. In mathematics, they are often called the building blocks of whole numbers because every whole number can be expressed as a product of primes. So where do these things appear in nature? Well, one of the most famous natural uses of prime numbers appears in the life cycle of certain periodic cicadas in North America. Not what I expected. These insects spend most of their lives underground, feeding on the sap of a tree. After a long development period, they emerge in massive numbers to mate. lay eggs, and die. The length of this cycle is either 13 years or 17 years, both prime numbers. And this isn't the only example. That feels like a coincidence, guys. Some species of bamboo flower at long prime numbered intervals, sometimes after 19, 29, or even 61 years. These extended cycles mean that the plants produce seeds at times that are extremely hard for seed-eating animals to predict. In both cases, the timing is not linked to an internal calendar in the way that humans track years, but to environmental and genetic controls that lock the species into these rare intervals. Using prime numbers in life cycles can help species avoid falling into a predictable pattern that matches the cycles of predators. Oh my god, nature's fucking clever, that's so cool. For example, if cicadas emerged every 12 years, a predator with a 4-year or 6-year population peak could match its life cycle to theirs, leading to heavy losses. However, with prime-numbered intervals like 13 or 17 years, overlapping with a predator's cycle becomes far less frequent. Even if a predator's cycle is close to the cicadas, the two patterns will not align perfectly for many decades, giving the cicadas a better chance to reproduce in overwhelming numbers without being completely consumed. That overlapping year, though, that's gonna be a beast! This strategy is known as predator satiation, which means that a species emerges or produces offspring in such huge numbers that predators cannot eat them all. Prime-numbered cycles make these mass emergences even more effective by reducing the chances that predators will be ready in large numbers at the same time. In bamboo, prime-number flowering ensures that seed predators cannot reliably time their reproduction to take advantage of the sudden abundance of food. Over thousands of generations, these rare intervals become fixed traits because they offer a clear survival advantage. While the Fibonacci sequence and the golden ratio receive the most attention, nature uses many other mathematical patterns to organize structures, improve efficiency, and create stable forms. These patterns are less widely known, but appear in everything from plant growth to geological formations and the surface patterns of animals. Lucas numbers. The Lucas numbers are closely related to the Fibonacci sequence, but begin with different starting values. Instead of starting with 1 and 1, the Lucas sequence begins with 2 and 1, then follows the same rule. Each new number is the sum of the previous two. This produces a sequence 2, 1, 3, 4, 7, 11, 18, and so on. Like Fibonacci numbers, Lucas numbers appear in phyllotaxis, the arrangements of leaves, petals, or seeds, but often in plants where the spiral counts differ from the classic Fibonacci pattern. Certain species of cacti show rib patterns linked to Lucas numbers. In the mineral world, Lucas numbers can appear in the symmetry of crystal growth, where the repeating units arrange in ways that reflect their mathematical relationships. Pascal's triangle. Pascal's triangle is a triangular arrangement of numbers where each number is the sum of the two directly above it. This simple structure contains many hidden mathematical patterns, including binomial coefficients, which have direct links to branching growth. In nature, Pascal's triangle connects to the way tree branches split, the layout of veins in leaves, and even how some flowers organize petals. The number of possible paths water can take through a branching network of streams or plant veins often follows patterns that can be found within Pascal's triangle. This connection arises because the triangle models how multiple possibilities expand layer by layer, much like a growing plant or a spreading river system. Triangular and hexagonal numbers. Triangular numbers represent objects arranged to form an equilateral triangle. Geometry! For example, 3 objects make the second triangular number, 6 objects comprise the third, and 10 objects produce the fourth. Hexagonal numbers extend this concept to hexagon-shaped arrangements. These arrangements are not only mathematical curiosities. Bees construct their honeycombs in hexagonal cells, which provide maximum storage with minimal wax. This is a geometric solution that minimizes wasted space and maximizes strength. Similar efficiency is seen in bubble packing, where soap bubbles naturally form hexagonal patterns when clustered. Basalt columns, such as those found at the Giant's Causeway in Northern Ireland, also form in hexagonal shapes when cooling lava contracts. These hexagonal arrangements distribute stress evenly, creating stable and efficient packing. Voronoi patterns. Voronoi patterns divide a surface into regions based on the distance to a set of points. Every point in a given region is closer to its designated seed point than to any other, producing irregular polygonal shapes that fit together without gaps. In biology, Voronoi patterns appear in the skin of giraffes, where each patch of color forms part of a natural polygonal network. Holy shit, I just thought it was different colored fur. Dragonfly wings also display a Voronoi-like geometry, with veins dividing the wing into panels that balance strength and lightness. On a geological scale, similar patterns emerge in cracked earth during droughts as the surface dries and contracts into irregular polygons. Inside living organisms, Voronoi structures appear in certain cellular tissues where each cell occupies the space nearest to its center of growth. But mathematical patterns do not stop at the edge of our planet. In the vastness of space, the same sequences that shape leaves, shells, and rivers are seen at a cosmic level. Many spiral galaxies, including our own Milky Way, display arms that curve in a way that is very similar to the Fibonacci spirals. This geometry helps maintain stability as stars orbit the galactic center and is created by the movement of matter through the galaxy over 1 million years. Then there's planetary resonance ratios. In our solar system, certain planets and moons orbit in resonance where their periods are in simple ratios. Jupiter's moons, Io, Europa, and Ganymede are locked in a 1:2:4 resonance, creating a predictable gravitational interaction. These resonances can stabilize orbits and influence planetary formation. But what about asteroids, the bane of planets? Bruce Willis. Turns out, even potential planet killers follow mathematical rules. Asteroid impacts on planets and moons create cratering patterns that can be studied statistically. While individual impacts are random, the overall distribution follows predictable probability patterns, showing how chance events can still create recognizable mathematical structures over long timescales. Mathematics is not just limited to symbols on a page, it's in nature, in space, and lives within every repeating cycle in the natural world. Thank you for watching. Sorry. Did you guys watch that TV show about the This isn't going to be funny to anyone else. Did you guys watch that TV show about the prime numbers, where that guy's trying to solve the prime numbers? I might have got really one night, and I was like, pretty sure I could figure that out. It's only funny to me because I remember how funny it was to me at the time. Oh my god, it's also super hot in here. I'm wearing this jumper and I'm going to take it off. I know it's going to break the continuity, but it's so hot. I started my day, it wasn't hot, and now it's hot. Editor, if that wasn't entertaining at all, let me know. You know, everything's a bit more entertaining when you...